One of the founding fathers of modern computation, John von Neumann, was responsible for major contributions to many scientific fields, including mathematics, physics, economics, statistics, and of course, computers. The most famous of his contributions in this field being the so-called von Neumann computer architecture, which consists of a processing unit that contains arithmetic logic units, or ALUs, and processor registers, a control unit which holds the instructions that are currently being executed or decoded, a memory which stores data and instructions, and input and output mechanisms. This concept, introduced in 1945, is basically the same that we use in most of today's computer architectures, like on the computer that you are using to watch this video. But von Neumann is associated not only with this computer architecture, but also with the inherent bottleneck that limits it. The so-called von Neumann bottleneck exists because the program memory and data memory share the same bus. Because the single bus can only access one of these two types of memory at a time, throughput is lower than the rate at which the CPU can work. This is a bottleneck that most of you will be familiar with, and I'm sure you've heard of the several mitigations that have been introduced over time to address it, from caches to branch predictors, and now with the advent of the system on chip. All of these focusing on data reference being local to the CPU. After all, if the data is close to the logic, we can reduce latency and increase throughput. But what happens when even such mitigations no longer bring greater throughput? What happens when the amounts of data we're working with are so large that it becomes impossible to further optimize the interconnects? AI datasets getting larger and larger, and with transistor scaling getting more limited, it seems inevitable that we will need a new computing paradigm, something that addresses the bottlenecks the von Neumann architecture left with us. Shortly before his death, von Neumann started to work on a book which he continued to write up until his last days, titled The Computer and the Brain. In it, he explored the possibility of creating computers that function more like the brain, which of course doesn't suffer from the inherent von Neumann architecture bottlenecks, and how to recreate brain-like functionality in the computer domain. Today, we call this neuromorphic computing, and as you're about to see, neuromorphic systems are the bridge that will connect us to the next age of technological evolution. If you'd like to expand your knowledge and get a deeper understanding of concepts like computer science, machine learning, and neural networks, today's sponsor Brilliant has brand new interactive content that will help you grasp these topics by solving puzzles and challenges in a simple and fun way, like this hot or cold puzzle from the Introduction to Neural Networks course. If you wonder how it is that computer vision can recognize and classify images, for instance, then this is the perfect course for you. If you want to go back to the basics and explore electricity and magnetism, Brilliant also has you covered with a great course that explains these classical physics themes, going from simple interactions between magnets all the way to how signaling between cells in your brain works. Improve yourself a little bit every day with Brilliant's goal-focused approach to learning and their interactive examples that take complex concepts and break them up into bite-sized, understandable chunks. Check out brilliant.org/cortex. You can sign up for free, and the first 256 people who do will get 20% off an annual premium subscription. Link in the video description. The very first question one might have regarding the brain is the brain a computer? There's a lot about the brain that we don't understand, but the bit that we do understand indicates that the brain is indeed a computer, but a very different kind of computer. It computes information that comes from inputs in a non-deterministic way and uses the results to control outputs, like using your vocal cords to produce sounds or using your arms and hands to pick something up. The fundamental principles and objectives that govern the brain aren't anything like the computers we have built, but ultimately it's still a computer. The second thing one might ask is, if the brain is indeed a computer, then how does it compute things? There are plenty of videos and literature out there that present neurons in a similar fashion to transistors, but unlike transistors, neurons are living things with their own agendas, so to speak. Neurons, unlike computer parts, are not components of your brain that are are used like transistors when needed. Neurons are living cells, living organisms. They are not controlled by a centralized entity, at least as far as we know. Dan Dennett, a professor of philosophy and cognitive scientist, compares neurons to termites in a colony. In the case of termites, they can build an artifact like these cathedral-like structures without there being an architect, or even a queen termite that directs all termites towards a common goal. Each individual termite is in fact clueless of what it is doing. It doesn't have a global view of the structure that it's building. A similar artifact, built in a completely different way, is the Sagrada Familia in Barcelona. It looks strikingly similar to some of these termite colony structures. Gaudí, the man behind the Sagrada Familia, created blueprints and manifestos for how the cathedral should be built and what it should look like, inside and outside. He then instructed his subordinates, issuing commands down the chain until eventually the stonemasons received their orders. So the Sagrada Familia is a top-down, hierarchical, pre-planned design, whereas we can see the opposite in the case of the termites. Unplanned design with no hierarchy, so a bottom-up type of design. The termites don't comprehend what they are doing, but they have the competence to build a structure almost as if they were being directed. So you can compare termites to neurons, whereas Gaudí's Sagrada Familia is more like a traditional computing system with clear directives from a central unit of command. Now, what scientists and philosophers alike are trying to understand is how is it possible that our brains are made up of neurons that act just like these termites, clueless individual units that have no idea that they are even inside a brain, yet we each have our own individual minds, which are cohesive and capable of working towards a single specific goal, which unite all of these neurons. It's a puzzling phenomenon, and we might never really find out how it all works. So again, if the neuron doesn't respond to commands from any central entity, how does it compute things? Well, the brain's computations are closely related to something you've probably been hearing a lot about: artificial neural networks, which are a way to mimic how the brain operates to some extent by using reinforced learning. But these artificial neural networks are software-based tokens of the biological neural networks. To build a computer that computes things in the same way as the brain does, we need to recreate the biology on hardware. This is the original ARM1 CPU. It was co-developed by Acorn engineers Sophie Wilson and Steve Ferber back in the early 80s. One of the pioneers in computer science, today Steve Ferber is working on neuromorphic systems and was responsible for conceptualizing Spinnaker, a neuromorphic system that has been helping neuroscientists understand how the brain works. Who better than to explain what a neuromorphic computer is and how the brain computes things? Steve, thank you for your time, first of all, and I guess the first question I have to ask is, what is neuromorphic computing?
Yeah, the word morphic simply means shaped a bit like neurons, so a bit brain-like, and the degree to which neuromorphic systems are influenced by what we do understand about the brain is highly variable. From many perspectives, Spinnaker looks like a conventional, massively parallel computer. So the big machine we have in Manchester has got 1 million processor cores distributed across 57,600 chips. But the aspect of the machine that's brain-inspired is the way we connect those cores together. In other words, how they communicate. And the key issue here is that in the brain, the connectivity between neurons is very high. Each neuron on average receives inputs from about 10,000 others. In some cases that number is much higher, and to achieve that in a computer with conventional communications is very messy and inefficient. So in Spinnaker we have a communication structure that's intrinsically multicast. When a neuron that's modeled on one particular core generates a spike, that spike becomes a packet, and that packet then flows out of that core and that chip and may land at thousands or tens of thousands of different destinations through the multicast routing fabric. So it's the connectivity really which is the brain-inspired aspect of Spinnaker.
Thanks to computers and modeling the brain, in the last 2 decades, neuroscientists have made profound advances in understanding the biological brain. And one area where we have gained some understanding is the 2 different types of networks that the brain switches between. We can refer to the thinking processes of these as the focused mode and the diffuse mode. The focused mode is associated with the concentrating abilities of the prefrontal cortex, which is located behind our foreheads. If your attention hasn't drifted off while watching this video, then your prefrontal cortex is engaged right now. This focused mode is switched on in your brain. The diffuse mode, on the other hand, is more associated with big picture perspectives. Diffuse mode is what happens when you relax your attention and let your mind wander. This relaxation of focus allows different areas of the brain to connect and return valuable insights. So while the focus mode is associated with the prefrontal cortex, the diffuse mode, as the name suggests, isn't affiliated with any one particular area of the brain. Some of you might remember that I compared these 2 types of thinking before to a pinball machine. In focused mode, your mind pulls back the mental pinball plunger and releases the ball, or a thought. The ball then bumps around the prefrontal cortex bumpers. There are so many bumpers packed together in this mode that the ball, or the thought, can become trapped in a cycle around the same region, when in fact it needs other areas of your brain to solve the problem at hand. The diffuse thinking process is useful here, as it's analogous to the ball starting to bump randomly against bumpers across the whole pinball table, or the whole brain, giving you that bigger picture perspective required for you to deal with a never-before-seen problem, or to learn a new thing. You can think of these bumpers as clusters of neurons. So if you learn how to play a few chords on the guitar, you can become better at it by using the focused mode and firing thoughts through the same paths until they become well-trodden paths, so that every time you pick up the guitar to learn new chords, if they are similar in shape to the ones you already know, a thought can travel through the same network pathways and make learning that much easier. This signal propagation is done in the brain using what we call spikes. And again, when it comes to relaying signals, the biological brain behaves like a very different computer compared to our digital machines. So what is a spike?
The spike is the primary mode of communication in the biological brain. So when a neuron is receiving inputs that it finds interesting, that it's learned to recognize, then it responds by emitting a ping, a pure asynchronous impulse, where all the information is conveyed in the timing of that ping and the neuron that issued it. So there's no detail, there's really very little information in the size or width of the ping. They're all the same shape. The timing conveys the information. And in Spinnaker, we abstract that spike or ping into a packet. And so the fact that a neuron modeled on a particular core has just spiked is conveyed as a packet through a packet switch fabric across the machine to many destinations. And when it arrives, it's treated as a pure asynchronous event. So the only information is which neuron it came from and when it happened.
So in the Spinnaker computer, all of the neurons and synapse models are implemented in software, running on relatively low-end small ARM cores, and all of the communication is reasonably conventional. What changes is the multicast aspect that Steve mentioned. So it's the communication aspect of Spinnaker what makes it neuromorphic or brain-like. So these spikes can be considered as a digital representation of results from the brain's computations. If spikes can be seen as digital, then this tells us something interesting about the brain. The biological brain is not purely analog. It's both analog and digital. But why is that, and how does that matter for the future of computers? As it turns out, not only does it matter, this combination of analog and digital might be the key to overcoming the end of Moore's law. Before World War II, the kinds of computers we built were purely analog in nature. What that means is that they used analog signals and analog computation. So using electric motors, you could turn shafts and cams, and the amount of rotations of a shaft, for instance, would correspond to the value of a variable. So if you wanted to calculate the trajectory of an explosive to shoot down an enemy warship at sea, you needed to measure several inputs like the advanced range and the speed at which your ship was moving, and the speed of the enemy ship, and wind speed and direction, and so on. Then you would enter those values into a mechanical computer and rotate shafts and cams according to these inputs, and get outputs giving you precise angles and direction to help you aim your weapons. These mechanical computers were invented because you could make these calculations in a few seconds, rather than days compared to the old tabulating machines. After World War II, in rough chronological terms, we started building digital computers like the ones we use today, which use digital signals and digital computation. This means the signals are not in ranges, but rather classified into two different outputs, true or false. Digital machines are therefore incredibly precise. If you want to communicate a very specific and clear signal, digital gives you that precision. But there's a problem with keeping both the computation and the communication digital. For instance, let's say you walk into a busy cafe and you spot an empty table. You walk over to the table and your brain sends out signals to have you sit your hot little rear end on the chair next to that table. Does the brain really need to calculate super precise values of the angle at which you will sit, precisely how much you should bend your knees, the exact rotation your body needs to do, how much you should lean forwards as you sit? No, that would require a ridiculous amount of calories to compute, and probably take you way too long to get that motion translated exactly right to your limbs. So instead, the brain sacrifices that precision, and using well-trodden signal paths that have been inside your brain since you were a child, you get a motion that will probably have you sit relatively accurately on the chair, and you will afterwards perform a few adjustments to get yourself comfortable. It's very rare that this calculation will be so wrong that instead of sitting down on the chair, you will miss it completely and land on the floor. So this trade-off of exact precision for a probabilistic output means that you will consume far less calories in performing this calculation and the corresponding movements. So one of the big lessons that nature is giving us here is that we could overcome the limitations of the impending end of Moore's law by applying these same principles in many areas of computation, particularly when it comes to efficiency and therefore managing heat in ever more densely packed transistors. So if we think about the biological brain as a computer, does that mean it runs software? Well, indulge me for a minute as I tell you a story. This was my very first computer. It's a ZX Spectrum. It was a very popular computer here in Europe back in the 80s, and it ran software on cassette tapes. So you would use a cassette tape recorder that would read these weird sounds that were recorded onto these tapes, which would convert them into ones and zeros on memory, and then once all of the program was loaded onto memory, the processor would run it and output it to a TV set, usually games in my case. As kids, my friends and I eventually realized that we could use regular tape recorders to duplicate the content of one tape to another, and thus save on buying new games. You know, piracy. And if tapes could be copied from one recorder to another, and if you could record music from radio airwaves using those same tape recorders, then why not broadcast games through radio signals so that other kids could tune in and share games through the airwaves? And thus started video game piracy over pirate radio, where you tune in to a certain frequency at a certain time, usually at night and usually using AM radio, and recorded the sound being played down to a cassette. You then get a working copy of a game for free. It was sort of like torrent piracy before the internet even existed. Well, that's exactly what's happening between my brain and your brain right now. I've just installed the shareware story called ZX Spectrum Piracy in the 80s from my brain to yours using a packet system called words. Words are incredibly powerful things. They are information packaged neatly in strange sounds, just like the software in those cassettes. And if we can transfer software like in my Spectrum story so easily between ourselves, then perhaps there's a way to tap into this ability and take it further. Perhaps we can find a way to do this process much quicker, so that instead of it taking 6 months to learn a new language, it can take 6 minutes or seconds. In theory, there's no reason why that wouldn't be possible, and we'll come back to that in a minute. But before that, why do we need to mimic the brain in this digital/analog way? Why not just use normal CMOS devices like in Spinnaker? After all, haven't chips become more and more efficient over time? To give you a better idea of the scale of the problem the industry is facing, let's plot this in a graph. Here you can see that 100 gigaops per watt is all that we can realistically air cool. Even Nvidia's new A100 GPU is still limited to 100 watts per gigaop. And judging by recent leaks, the same should be true for AMD's upcoming MI100 Arcturus GPU. So there's a clear bottleneck in terms of power consumption, which is quickly slowing down progress in this type of hardware. A lot of people were surprised that the A100 was delivering a modest improvement over Nvidia's last generation hardware, and here you can see why that is the case. Contrary to what the marketing departments at Intel, AMD, and Nvidia are trying to sell us, current CMOS cannot run future AI. I recently covered the A64FX from Fujitsu, a system that combines the capabilities of a CPU and a GPU to address some of the bottlenecks we are currently facing, like power and memory bandwidth. But even Professor Matsuoka admits that there will need to be a change in paradigm soon because we will quickly hit a wall. In fact, there are two fundamental walls that we've hit with traditional CMOS, the power wall and the memory wall. The power wall simply means we cannot dissipate the amount of heat that's generated in processors because of the density of transistors. This is something you are probably aware of already if you've been following my channel. If we place the human brain on the chart, you can see that not only is it magnitudes faster at the same types of computations, if we can call them that, but also consumes a tiny amount of energy in comparison, roughly 20 watts. This summer, I suspect we will be hearing a lot about novel packaging techniques that will continue to drive performance increases. But even these cool advanced packaging techniques are transitionary steps. They will quickly be exhausted. They will buy us another 5 to 10 years, hopefully. But what will we do after that? The fundamental problem, and perhaps a dogma that the industry should face, has to do with the underlying architectures that we are using in our computers today. Not only can neuromorphic systems help us address the power wall, the memory wall can also be overcome if we model our future computers on some aspects of the brain. One important recent discovery is something called a memristor, which can be represented like this. So here we have the resistance as a function of voltage, and at the bottom you have the on state at a certain resistance, then intermediate values, and then we reach a point where the resistance represents an off state. These intermediate values give us that analog property of synapses, which aren't simply ones or zeros like in digital computers, but can be a range of values. So by changing the voltage, you can control the resistance and therefore simulate a synapse. But note that when you bring the voltage back to zero, the value is kept in memory. So this works as both a valve but also as memory, which is a clever way to keep memory close to logic. If this is going over your head, the important thing to keep in mind here is that unlike traditional computers where you have ones and zeros and volatile memory, with memristors we can create a range of values beyond just 1 and 0 and keep the data stored locally. There are several ways to achieve this. There's filamentary switching, phase change, and ferroelectric, some of which I've covered in the past. Whichever one you decide to use, it's likely that we will see 3D structures being used here as well. So in a preliminary stage, you'd have traditional CMOS at the bottom of these devices, several layers of memristors stacked on top, and then vias to connect them. So what you are looking at here is basically a neural network implemented in hardware. Experimental hardware based on this new paradigm has shown that memristors can be 100 times faster than GPUs while consuming 100 times less energy. What this means in practical terms is that something like the original implementation of NVIDIA's DLSS technique could be done locally on your machine in the future using a neuromorphic GPU instead of relying on NVIDIA's servers to do all the computations that were required to train the AI. To be able to scale up the game's visuals from 1080p to 4K, for instance. We will be able to increase ray tracing performance significantly with co-processors and new types of memory, sure, but at some point in the next decade, we will need to rethink the whole underlying architectures, and the new generation of DLSS implemented in hardware will be fundamental to drive our games at 8K and 16K with realistic real-time path tracing. Neuromorphic GPUs are probably the answer, putting the equivalent of a warehouse full of NVIDIA servers inside a GPU chip or a co-processing neural chip. Another approach to creating a neuromorphic system is by using one of the most promising technologies that are being researched, photonics. Photonics simply means that we use light to make the connections between neurons and synapses, rather than copper wires. One of the interesting aspects of using optics in computing is that you can vary the wavelength, which means you can multiplex and distribute a lot more data that way. This would in turn allow for the creation of state-of-the-art deep networks in huge scales. As a paper in Nature issue 569 from last year shows, there are many groups working on photonics from Intel to small startups, and it's a topic that I might cover in more detail in the future. In addition to using wires and light, another way to connect neurons and synapses would be using magnets and radio waves. This is where spin torque comes into play, and there will be some devices introduced this year by companies like TSMC that integrate this technology for different purposes, specifically on-chip memory. So that's a lot of information to take in, and I guess the thing you might be wondering is, when will we have neuromorphic computers then? Well, we already have a few early examples, and many more are on the way. We already looked at Steve Ferber's first machine, Spinnaker, and a new version aptly called Spinnaker 2 is now nearing completion.
The current Spinnaker machine, which we now call Spinnaker 1, has been around for nearly 10 years, in prototype form for more than 10 years, but at the chip level since 2011, and we've been steadily scaling it up. So the big million-core machine, which was our original objective, went online in November 2018. The second generation machine, which is based considerably on our experience with Spinnaker 1, is currently in prototype form. So we have some small-scale prototypes in the lab. We're co-developing it with our HBP partners at TU Dresden. The design of the full chip is now complete, or approaching completion at Dresden, and is likely to be fabricated over the next year or so. So in 2021, we should see small to medium scale Spinnaker 2 machines becoming available. The big difference between Spinnaker 1 and Spinnaker 2 is the process technology. Spinnaker 1 is 130 nanometer CMOS, which was quite old even in 2011. Spinnaker 2 will use a 22 nanometer FDSOI technology, and that allows us to increase the number of cores on the chip from 18 to 152. And so we're aiming for sort of 10x performance, functionality, and energy efficiency on Spinnaker 2.
So while Spinnaker 1 was capable of achieving about 1% of the human brain's capacity, Spinnaker 2 should reach about 10%. Again, it's important to understand that Steve's machine has been built for research purposes, so that we can better understand how the human brain works. It's of course an ARM-based machine, so perhaps NVIDIA will get involved in the third version of Spinnaker. Another neuromorphic chip was introduced with great fanfare by the former Intel CEO, Brian Krasnick back at CES 2018 a chip called Loihi. This chip has 128 neuromorphic cores fabricated on Intel's 14nm process. And similarly to Spinnaker, this is an event-driven parallel compute device, so it also sends spikes along the many cores to activate synapses. When a bunch of spikes accumulate for a certain period of time and reach a set threshold in a core, the core will fire off its own spikes to its connected neurons. This promising chip is a research platform for Intel and is programmable. Much like Intel's upcoming line of GPUs, XC, Loihi chips can be organized in tiles, and one such system, called Pohoiki, consists of 768 Loihi chips for a total of 98,000 cores, or just over 100 million neurons. Unlike a traditional system configured to handle neural networks with CPUs and GPUs, Pohoiki doesn't need to transfer data and instructions around to memory. This means Pohoiki is many times faster and more energy efficient than something like an NVIDIA DGX that uses GPUs for AI learning and inference. The whole Pohoiki Spring system, with all its 98,000 cores, uses a mere 300 watts. In a study done in Canada by Applied Brain Research, a team of researchers testing the recognition of phrases like "Hello Siri" compared a Xeon E5-2630, an NVIDIA Quadro K4000, an NVIDIA Jetson TX1, and a Movidius NCS to a single Loihi Wolf Mountain board. Intel's Loihi-based neuromorphic system was magnitudes more power efficient than the popular alternatives and had about 8% more accuracy. This shows the tremendous potential of neuromorphic chips, especially for power-constrained applications like micro and nanobots, wearables, IoT, etc. Speaking of low-power wearables, Prophecy, a neuromorphic system from France, is looking to solve blindness through vision restoration using a neuromorphic vision chip. Thanks to the small size and lower power usage, Prophecy is developing microelectronics that should be able to replace damaged cells in the biological brain in the coming years. But even before we get to that micro level, we can perhaps finally see chips added to augmented reality glasses, small enough not to make you look even more like a dork, and maybe even chips small enough to perhaps fit into a contact lens. It might sound like science fiction, but thanks to a new paradigm of event-based vision rather than frame-based vision, along with chips that mimic the brain, those cool augmented vision interfaces we've seen in movies and video games might become a reality within 10 to 15 years. Perhaps that will be the next iteration of phones, going from devices in our hands straight to our eyes. The famous author Ray Kurzweil talks about this concept called the paradigm shift rate, which essentially means that there's an exponential growth in technology that is requiring new business models and the convergence of several technologies at an ever-increasing rate. A famous example of that is if we look at the hand axe. It's estimated that this tool was used by humans for 1.5 million years. Now look at a similarly shaped tool, the mouse. How long did it take our most commonly used interfaces switching from the mouse to touch screens? We eliminated the need for the mouse just a few decades after its introduction. So a few minutes ago I told you my story about the ZX Spectrum and transferring games via sounds, or rather signals in the airwaves. Well, our genes are strings of data. They don't necessarily need to be represented in the way biology represents them. They can be translated into other formats, just like we exchanged software via airwaves to cassette tapes back in the 80s. The human brain too can be enhanced by receiving software updates, so to speak. Companies like Elon Musk's Neuralink have set their long-term targets at such brain enhancements. In the short term, biotechnology aims to reprogram biology. Our biological bodies are not programmed to recognize cancers, for instance, but with nanotechnology, we will reach a point in the next couple of decades where we can reprogram our bodies to do so, reverse engineering the brain, as great pioneers of neuromorphic computing are doing, like Steve Ferber or Carver meet will allow us to treat mental illnesses like depression and anxiety, and in the future to enhance the biological brain. I discussed these and many other topics with Steve Ferber regarding neuromorphic systems in the brain, from nanoscale applications to consciousness and even to the singularity. The full discussion will be available to my patrons, so join my Patreon if neuromorphic systems spike to your interest. There are great advances in technology and chip design on the horizon, with new forms of packaging chips, new types of memory, quantum computing, and many other exciting things. But it's undeniable that CMOS is reaching its limits under the current architectural paradigms. Ventures like Loihi, Brainscale, Spinnaker, BrainChip, and others are leading the charge, but the semiconductor industry as a whole will need to rethink some of its guiding principles in the coming years, and perhaps an evolution from the old von Neumann architectures to neuromorphic systems will be the bridge that will take us beyond Moore's law and from the electronic age to the deep tech age, something that we will be discussing in future videos. Make sure you subscribe so you don't miss them. A big thanks to Steve Ferber for his time and patience in answering all of my questions, and a huge thanks to my patrons for keeping this channel going. Join my Patreon today and get exclusive access to the Cortex Discord server, to the background music used in my videos, and to exclusive content, like the full discussion on neuromorphic systems with Steve Ferber. Your support makes a world of difference, so join my Patreon today. Thanks for watching, and until the next one.